Hello everyone. Today's video will show you how to design a calculator with addition, subtraction, multiplication, and division, and display the result on a 7-segment display. This project will reuse the block design from the previous section. So, first we open project number 3. In order to avoid overwriting project number 3, we save this project as a new one. We can name it number 4 calculator. Then, just like in the previous section, we need to create our own RTL to implement the functions of the calculator. Select Create AXI Peripheral and rename the IP. This time, we can enable interrupt support, as we might use this port for our next project. Select Edit IP to modify it. Here we can copy the code from my website first, and I will expand the code later. The input-output ports of this IP are the same as in the previous project, so just copy the AN out and SG out for the 7-segment display as we did last time. For this project, we will need one register to store the output result of the calculator, so we comment out the assignment of register 3 in the original AXI interface. We will assign this signal ourselves later. Let's quickly copy the other files. For display control, we will use the same RTL from the previous project. We need to deselect the Copy Sources into IP Directory option. Okay, so let's take a look at our code. First, we create a new module called Calculator Core. This module takes the input digits and operation directly from the AXI registers. We store the 4 digits in register 1 and the target operation in register 2. The operation here might be addition, subtraction, or other operations. When it finishes the calculation, it outputs the result in calculation answer, along with a flag called calculation done. Then, because the result is a single number in binary format, we need to convert the number to a 4-digit format to display on the 7-segment display. To do this, we need a BCD to 7-segment display decoder, which we name number to digit here. This module takes the inputs from calculator core and converts them into 4 separate digits. Here we have a simple max to select which data will be shown on the 7-segment display. If the calculation is not done, we display the numbers we key in, and if the calculation is finished, we display the result. As mentioned, we use register 3 to store the result, which can be read out by microblades and displayed on our computer. Lastly, we use display control from the previous project to display the number on our 7-segment display component. So to sum up, as you can see in the block diagram here, we key in our digit and operation, calculate the result, store the result in register 3, convert the result to a 4-digit format, and use display control to display it on the 7-segment display. Let's take a look at the calculator core. First, we define a few parameters, including a small finite state machine to control the states of our calculator. Next, we define parameters for different operations. Here is the finite state machine. After we key in our first digits and press an arithmetic operation, we jump to the wait state to wait for the next digit to come in. After the next digit are entered and we press enter, we jump to the next state to calculate the result. After one cycle, we output our result and wait for escape to start a new round. This part contains simple logic to convert 4 digits into a single number. Here's how the calculator works. We first store the first number into calculation answer during the idle state. During the calculation state, we perform the corresponding operation and store the final result back in calculation answer. Please note that the multiplication and division operations here require very large circuits, so we need to be careful when using them. Since this is a simple project, we won't optimize them this time. Lastly, here is the sequential part. There's a signal called operation store that holds the arithmetic operation. Otherwise, the operation will be overwritten when we press enter. We assert the calculation down signal when the finite state machine is in the output state. Now let's take a look at number 2-digit. First, we define a few parameters for a finite state machine that implements the Dabble algorithm. This module performs the Dabble algorithm, which is used to convert a binary number into separate digits. I won't elaborate on the algorithm here. You can check out other videos that explain it in detail. In here, we expand the input number into 4 digits parts. Since each digit ranges from 0 to 9, we only need 4 bits to store each digit. Finally, we output the 4 parts as our final result. Then we can run synthesis to check if everything is correct. Next, merge all changes and click Repackage IP. Now we are back to the main design. We can add the IP, search calculator, delete the display control and replace it with our calculator control. Reconnect the wires. Now, our design for today's project is complete. We generate the HDL wrapper and run generate bitstream. Here we can see that there are timing violations because the multiplication and division functions require very large circuits, especially since we perform them in just one cycle. The violations might be okay because this is not a complicated project. We will leave these violations aside just for now. After bitstream is successfully generated, we can export the hardware as usual and launch the Vitis IDE. Let's quickly create a platform and one empty application as usual. Now you can copy the C code from my website, rename the file. Next, let's take a look at the C code. First, we define the parameters for each register. Here we have a function called waitResult. After we finish our operation, we need to wait for the result by continuously reading register 3 to check if calculation done is asserted. If it is asserted, we can display the result on our computer. After the calculation is complete, we need to press escape to start a new run. So we define another function to wait for escape called waitEscape. We can also terminate the process by pressing escape at any time. Here is a function for waiting for escape. In the main function, we first write the initial values and detect the computer's input. We decode the ASCII code inputs and write them into the corresponding registers. Every time we press an operation, we need to clear the data so that the 7-segment display can show the next input number. Then we can build and run the project on our Basys 3 board. As you can see, the calculator is working properly. For large numbers that cannot be displayed with just 4 digits, only the least significant 4 digits will be shown on the board, but the correct answer can still be seen in the computer's display window.